Progressions is the topic which we are going to discuss for the session. What is progressions, or how do we define that in mathematical terms, is the biggest question out here. As we have been coming across many situations in real life of patterns. For example, I have a number 3 and then a number 5 and a number 7. Then immediately I can say that based on 3, 5, 7, my next number is 9, 11, 13. So from the first 3 or 4 terms, I can identify the 5th or 6th term, which we can easily identify through a pattern. Therefore, here to start with the topic of progressions, progressions is nothing but a pattern. Anything which follows a pattern comes under progressions. The pattern can be either, for example, if I take 2 squared, 2 cubed, then immediately I can say the next term is 2 power 4, because I can say this because I know that the first 3 terms are following a certain pattern. Therefore, 2 squared, 2 cubed, 2 power 4, 2 power 5, 2 power 6 is how I identify the pattern. So with the minimum information given, if you can identify the extended part of it, is what is called a pattern. Let's try some practice problems in identifying the pattern. Then I would like to know the next term in this pattern. I clearly see that when I add 4 to 1, I get 5. When I add 4 to 5, I get 9. When I add 4 to 9, I get 13. Therefore, when I add 4 to 13, that is 13 plus 4 equal to 17 is the next pattern, followed by 21, 25, etc. So every problem need not be with the same pattern. Different problems come out with different pattern. For example, here all terms are raised to integral powers with respect to integers. Here each of the term is added with 4. So like this, we have different patterns which follow different sequences in identifying whether adding of 4 or raising it to power 2. Let's try some more problems for practice. For example, I have how do I know the next term here? So all patterns are not easy because some patterns are easy to construct, but some patterns are very complex. Say for example, with this example problem 1, 3, 6, 10, etc. So my first term is 3 and my second term here is 3 and the third term 6 and the fourth term 10. Then what is the fifth term is the biggest question of the problem. So what do we get in the next followed pattern? Identifying the pattern is very important than writing the pattern out here. So what would be the next term out here? What kind of a pattern does it follow is what we're going to see. So let's see here. As I see the first term, this is 1, and as I see with the second term, this is 3, which is 1 plus 2, and as I see with the third term, this is 1 plus 2 plus 3, because each of the integers are added respectively in each of the term. 3 plus 2, 5 plus 1, 6, 2 plus 1, 3, and 1. And finally, my 10 is 1 plus 2 plus 3 plus 4. When added, 4 plus 3, 7, 9, and 10. Therefore, my next term is set to follow the similar pattern with 1 plus 2 plus 3 plus 4 plus 5. So therefore, my next term which has to be found will be 1 plus 2 plus 3 plus 4 plus 5, which gives me 15. So 15 is the next term of the pattern, is how we identify. So there might be various forms in mathematics or the mathematical properties through which patterns exist. It is very important to identify the exact pattern which the mathematical terms follow. In this case being 1, 1 plus 2, 1 plus 2 plus 3, etc. 15, and then comes 21, etc. is how we identify the pattern here. Now let's come to the most important pattern in mathematics called the Fibonacci sequence, which is still a mysterious fact in mathematics. So let's see what the Fibonacci sequence says in its own terms. To start with, 0, 1, 1, 2, 3, 5, etc. So what kind of a pattern is this, and what are the next terms in the pattern is what we are going to identify here. This sequence is called Fibonacci sequence, one of the most important sequences in mathematics, connecting the golden ratio with it. So how do we identify the pattern here? Here it has been 1, 1 plus 2, 1 plus 2 plus 3, etc. And here it has been adding of 4 each time. And here it has been raising of the power 2 each time the sequence proceeds further. Then how do we identify the pattern here is the biggest question for the problem. So in this case, as I see here, when I take the first two terms, when I add the two terms, 0 plus 1 is 1. So when I add the first two terms, it gives me the next term. And when I add these two terms, it gives me the next term. That is, the next term is obtained by adding the previous two successive terms. That is, as I see here, 0 plus 1 is 1, and 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. Therefore, we can guess the next term being 3 plus 5. Therefore, I get this as 3 plus 5, which is 8, is the next term. And then finally, the next term will be 5 plus 8, which is 13, etc. So this kind of a sequence where the next term is the sum of the previous two terms successively is called a Fibonacci sequence. The terms being 0, 1, 1, 2, 3, 5, 8, 13, etc. is called a Fibonacci sequence. So this kind of different types of sequences is what we are going to discuss in this today's session of progressions. The other word for progressions is following of a pattern. So let's see the different problems followed with different patterns out here. Now let's see how the progressions has come into existence with the real life situations. Progressions are generally used in everyday life. Unknowingly, we don't know that we are using the concept of progressions, but we use progressions in daily life very much. The applications of mathematics in daily life. For example, I go to a bank, then most of the banking transactions happen through progressions. As we can see here, for example, I go to the bank where I deposit a sum of 5,000 rupees in the bank. So when I deposit rupees 5,000 in the bank, the bank gives an interest of 200 rupees every year. Say for example, for the amount of 5,000, the bank interest per year is rupees 200. That is, every year uniformly there is 200 rupees which is increased as the interest for the deposited amount of 5,000. So after 6 years, I want to go and collect my money. So if I go after 6 years, what will be the amount of money? How much is the money I collect? Do I collect is the biggest question here. So after 6 years, definitely the money increases because the interest rate is 200 per annum or per year. And after 6 years, how much money do I collect? These are the transactions which we do in everyday life. Every household deposits money in the bank, and we use, interestingly, the progressions or the patterns in case of this real life situational problem. How do we use it is the biggest question for this real life problem. As I see here, I can see that in the first year, my deposit of 5,000 increases with 200 rupees as the interest. Therefore, this comes out to be 5,200. And therefore, my second year will have another 200 added to this, So I get 5,400, then 5,600, 5,800, so on and so forth. Therefore, let's start with second year, where this amount is added with 200 because the bank gives an interest of 200 rupees per annum. So this gives me rupees 5,400. Again, in the third year, 200 is added to this. So I get 5,600, 5,800, 5,000, 6,000. So 1, 2, 3, 4, 5 and 6,200 is the amount which finally collects in the third year, fourth year, fifth year and sixth year. Now in the sixth year, this amount accumulates to rupees 6,200. That means by the end of the sixth year, I'm going to collect an amount of 6,200 years. For the initial amount which I deposited is 5,000 rupees. That means I'm at a profit of 1,200 rupees because the difference is 1,200. I'm at a profit of 1,200 rupees when I deposit the amount in the bank and remove it after 6 years. So this is how we understand the patterns in real life. Why do we know that this is increasing by 200? Because by the first 2-3 terms, we follow there's a pattern where every time it increases by 200, the amount increases by 200, and finally we get a pattern with this. This is an example of a pattern or a progression used in daily life. Now that we have seen various types of patterns in our example cases, we have many patterns in mathematics which have their own respective ways of identifying the different numbers in the patterns. But here, the two important patterns which we're going to discuss in the syllabus are the arithmetic pattern and the geometric pattern. So in progression, there are two types of progressions which we are going to discuss mainly in the session. So the two types are the arithmetic progression and the geometric progression are the two types of progressions which we are going to discuss in the session. So here, as we have identified that a progression is a pattern, therefore an arithmetic progression and geometric progressions are also the different types of patterns with their respective definitions. So let's see each of the progressions in detail with their own definitions. But before that, generally an arithmetic progression is denoted with the abbreviation AP, which stands as arithmetic progression. And then a geometric progression is denoted with GP, which stands for geometric progression. So to start with the arithmetic progression. So what is an arithmetic progression? The first type of progression or the pattern which we're going to study. So what is an arithmetic progression is the biggest question out here. So an arithmetic progression is a pattern in which a fixed number is always added to each of the terms. So therefore, to understand this more clearly, let's take the definition. A pattern which has fixed element added to each of its term is called an arithmetic progression. So what do you understand by a pattern which has fixed element? Now this is a very important role which plays in arithmetic progression. So pattern which has fixed element which added to each of its term. Let's see with an example. For example, I take a pattern 1, 5, 9, 13, etc. This example has already been discussed, where let's again revisit the same example problem. Now if I take the pattern 1, 5, 9, 13, 17, in this case, what is the fixed element which is added? Now as I see here, let me rearrange so that my first term is 1, but my second term is obtained by adding 4 to the previous term, Next, my 9 is obtained by adding 4 to the next previous term, which is this. So this is added here, and this is added to this, and next 9 plus 4 will give me 13, and 13 plus 4 will give me 17, and 17 plus 4 will give me 17, etc. That means, as I see here, this is reduced to this form, where 5 is written as 1 plus 4, 9 is written as 5 plus 4, 13 as 9 plus 4, 17 as 13 plus 4, which makes me understand that every element is obtained by adding 4 to the previous term. 5 plus 4 gives 9, 9 plus 4 gives 13, 13 plus 4 gives 17, 17 plus 4 gives 21, 21 plus 4 gives 25, is how we get. Here, this strictly follows the definition that this is a pattern which has fixed element, which is 4, added to each of its term. Now in case of this example problem, I see that the fixed element 4 is added to each of the term of the given progression or a pattern. Therefore, this kind of sequence where a fixed element is added to each of the terms is called an arithmetic progression, as given by the definition. The fixed element here is 4, is what we identify in an arithmetic progression, this being one of the example. Let me take one more example. Is this an arithmetic progression? Is the question out here. Yes, it is, because every element is obtained by adding the fixed element 0 to the previous term. Therefore, here the fixed element is 0, which gives me 7 plus 0 as 7. So, because I can add the fixed element 0, I say this is an arithmetic progression, and this is also an arithmetic progression. The only restriction out here is that fixed element must be added to each of its term. You need to identify a fixed element added in each of its term. Fixed element added in each of its term is how we identify the arithmetic progression in its own definition. Now, let's see the general form of representing the arithmetic progression. Now that we have defined what kind of a pattern makes an arithmetic progression, now next comes with the concept on how we can solve many of the problems involving arithmetic progression. Now in that case, initially I start with the general form of representing an arithmetic progression. So the general form of representation of arithmetic progression is done generally by taking in the form A. Now because the pattern says that there is a fixed element added to each of its term, let me take the fixed element as D. So I take the fixed element which is added to each of the terms as A plus D and A plus D plus D, because it is added to this, and this becomes A plus 2D plus D is how I get the pattern. Because every time I add D to the previous term, because A plus D plus D is A plus 2D, and I get like this. So that this on further modification gives me A plus D, A plus 2D, A plus 3D, A plus 4D, and so on and so forth, is how we get the pattern. But it cannot have infinitely many terms, because if I say it is the first n terms, then it reduces to A plus n minus 1 into D. The reason being that my second term has 1D, my third term, first, second, third term has 2D, 1 less of 3, my fourth term has 3, 1 less of 4, fifth term has 4, so my nth term has n minus 1. 1 less than n. So therefore, my nth term would be a plus n minus 1 times of d, following with the pattern, is how we get this general form. This is called the general form of representing the arithmetic progression. So this is the general form of representing the arithmetic progression, where a is called the first term and d is called the common difference, because every time you take the difference, I get d. The difference of this is d, the difference of this is d, the difference of this is d, and the difference of this is d, so on and so forth. I get a common difference every time. The difference is always same. Therefore, d is called the common difference for the given arithmetic sequence, is how we identify each of them. Now, in this case, my first term is denoted generally with a1. That means the first term is a, which is a1 equal to a. Similarly, my second term of the arithmetic progression in general is denoted with a2, and a2 stands for second term. Therefore, the second term, first and second term, is a plus d. Therefore, my a2 is a plus d. And similarly, my third term a3 will be a plus 2d. Therefore, the third term a3 is a plus 2d, and similarly my fourth term a4 is a plus 3d, and so on. My n minus 1th term, denoted by a n minus 1, will be a plus n minus 2 times d, because my nth term is n minus 1d. So my n minus 1 term is n minus 2d plus a, of course, denoted by a minus 1. So finally, my last term, which is the nth term, is an equals a plus n minus 1 times d. Is how we identify the formula in general. The nth term is an equals a plus n minus 1 times d. The first term is a, the common difference is d, the nth term is this. So the general form of arithmetic progression is denoted by a plus d, a plus 2d, a plus 3d, so on and so forth till a plus n minus 1d, where a is the first term, d is the common difference, and a plus n minus 1d denoted by an is the nth term, is how we understand the arithmetic progression through the basic formula. Now here, the common difference d is generally the difference of the term minus its previous term, because if I wanted to get d, a plus 3d minus a plus 2d gives me d, and this minus this gives me d, or this minus this gives me d, or this minus this gives me d, which makes me understand that the common difference d is given by the formula nth term minus its previous nth term, that is a n minus 1, is how we identify the formula of d. The common difference is given as the term minus its previous term. Can also be read as term minus previous term or immediate previous term. The successive previous term is how I get the formula for the common difference. Now let's see an example problem and identify the first term, the common difference, and the nth term. So for example, I take the sequence minus 17, minus 12, minus 7, minus 2, 3, 8, and so on and so forth. So in this sequence, the first and foremost thing I need to identify is whether this follows a pattern, or whether especially this follows an arithmetic pattern. In order for this to follow an arithmetic pattern, we need to identify the difference. If the common difference is same, then we say that this pattern is an arithmetic progression. So let's identify this for the common difference. So if I take this problem, I clearly identify that the difference of this and this is minus 12 minus of minus 17, which is 17 minus 12, which is 5. Therefore, when I add 5 to minus 17, I get this. When Phi is added to minus 17, I get this. Similarly, I find the difference of this and this also as plus phi. This also as plus phi, plus phi, plus phi. Now since the common difference is the fixed number is same, therefore clearly I can say that because each of the difference is same, this is an arithmetic progression, is how we identify the pattern. The first initial stage of the identifying of the pattern is identifying their difference. Now since each of the difference is fixed, therefore since the common difference is fixed, that is I get phi, therefore the given pattern forms an arithmetic progression denoted by AP. Now since the common difference is fixed, therefore the given pattern forms an arithmetic progression fixed with the number phi, fixed at number phi. Now in this case, since this forms an arithmetic progression, I have the first term a1 which is denoted with negative 17, and my second term which is a plus d in the general form is denoted with negative 12, and my third term a plus 2d is denoted with minus 7. Similarly, my fourth, fifth, sixth and all terms are denoted with a plus n minus 1 into d. Now in this case, my first term is a, therefore my first term a is minus 17 is how I identify the first term. And the common difference d is nothing but the term minus previous term. Therefore I can take a2 minus a1 or a7 minus a6 or a99 minus a98 or an minus an minus 1. Finally, because I know the first two terms, I take a2 minus a1 and I get this to be minus 12 minus of this, which is 5. Therefore a is minus 17 and d is 5. So here I get a is negative 17 and d is 5. The first term is minus 17 and the common difference is 5. Then how do I find the nth term? I know the first term, I know the second term, I know the third term, fourth, fifth and sixth, but how do I find, if suppose I wanted to find the 100th term, how do I find the 100th term is the biggest question. So in case of such problems where I wanted to find the 100th term or the nth term, I use the formula for nth term in this form. So in this case, I have my nth term is denoted by an, and the formula for an, which is the nth term, is given by a plus n minus 1 times d. This is the formula for finding the nth term, a very important formula. So let's see how the nth term is obtained. So when I substitute this, then a is nothing but negative 17, which I'm going to substitute in place of a as negative 17 plus n minus 1 times of d, which is 5, which I substitute in place of d. And because we don't know n is fixed as n. Now in this case, I get this as minus 17 plus 5n minus 5 is what I get. Therefore, an is 5n minus 17 minus 5 is minus 22 is the nth term of the given sequence. Is how we get the first term, the common difference and the nth term. Now next, suppose I wanted to find, say, the 100th term. So I wanted to find the 100th term is how much? Without adding them 5 all the times till 100 times, I can directly use this formula to find the nth term or the 100th term. or the 1000th term or 1 croreth term, however big, we can just do it in fraction of seconds. And that is the significance of arithmetic progression and its formula. So in this case, the 100th formula, which is denoted by A100, is given by 5 times, or I can do this by taking A plus 99D, because A plus 99D is one short of this, A plus n minus 1 of D. So 100, one short of 99. So this would be nothing but A, which is negative 17, plus 99 times of D, which is 5, which on simplification gives 9 5s 45, 9 5s 45, 49, 495 minus 17, 478 is the term. 495 minus 17 gives me 478. Therefore, the 100th term of the sequence is 478, is what I got by just solving it in two-step process. So arithmetic progression has its own applications in many of the branches where we use the formulae, the first term, the common difference, and the nth term. Now let's see the reverse process of understanding the arithmetic progression, where if a pattern is given, I can identify the first term and the common difference, and of course even the nth term for an arithmetic progression. But what if I give only the first term and the common difference? Can we construct the whole of the sequence using only A and D is the biggest question out here. So let's see the reverse process. Let's take an example problem here to understand the reverse process of constructing the whole of the arithmetic progression just from the minimum information of the first term and the common difference. So my question here is, if the first term is minus 65 and the common difference is 7, then how do I construct the arithmetic sequence? Then construct its respective arithmetic progression is the question out here. So in case of this problem, I identify my first term, which is denoted by A1, is A, which is minus 65. The first term is generally denoted by A, which is minus 65. And the common difference is 7, implies D is 7. So D is 7 and A is minus 65 is what we get. And the question is to construct the respective arithmetic progression. We can do that because if we revisit the general arithmetic progression which we have considered is A plus D, A plus 2D, A plus 3D, so on and so forth is what we get as the sequence. Now in case of this, because I know A and D, I'm going to substitute in each of the terms where I get the whole of the sequence. So let's see how the sequence is obtained. Initially A is negative 65, then the next is A plus D, which is negative 65 plus 7, then it is A plus 2D plus 2 times of 7, so on and so forth. Now this, on further simplification, gives me negative 65. Negative 65 plus 7 is nothing but negative 58. Then negative 58 plus 7 is negative 51, plus 14 is negative 51, and this gives me 44, because minus 65 plus 21 is negative 44, and so on and so forth. So this is how the sequence is constructed using the first term and the common difference. can be constructed. So like that, given the sequence, I can find A and D, and given A and D, I can find the sequence where the first term is minus 65, the second term is minus 58, the third term A3 is minus 51, and the fourth term A4 is minus 44. My 17th term A17 also can be found, because I don't know here, I cannot always construct till 17 times. So my 17th term, say for example, I would like to find the 17th term, A17 is nothing but A plus 16D, one short of 17. Therefore, this comes out to be A, which is minus 65 plus 16 times of D, which is 7. And then I get the answer obtained from there. So that this reduces to negative 65, 6 sevens, 7 ones, 112, 70, 42, 47 plus 47 is the answer. So my 17th term is 47 in the given sequence, somewhere lying here, is how we understand the concept of arithmetic progression connected with the first term, the common difference, and the nth term an, a plus n minus 1 times d. Now that we have seen the definition of arithmetic progression with its respective formulae, now comes the types of arithmetic progressions. Generally, there are two types of arithmetic progressions identified in mathematics, the branch of mathematics. One is the finite arithmetic progression, and the other is the infinite arithmetic progression. So coming to this, it is the finite, and the other is the infinite arithmetic progressions which we deal with. What is an infinite arithmetic progression, or what is a finite arithmetic progression? So for example, if the terms are finite, in case of finite arithmetic progression, there are finite number of terms. That means you can count them, they are countable. So the finite number of terms which are countable are said to be finite arithmetic progressions, and in infinite arithmetic progression there are infinite number of terms which are uncountable, very large. Infinite number of terms which are uncountable is what we identify the difference between finite and infinite. So let's take an example to understand the finite and infinite arithmetic progressions. So when it comes to understanding the finite arithmetic progression, as the definition clearly says that the number of terms are finite which are countable, then we take only those terms which are limited. Here they are unlimited. So for example, I take the amount I deposit in the bank is 500, then again it increases to 600 or doubles up every 5 years. So it becomes 1000, and then it becomes 1500. So every time it is 500 rupees increased. So 2500. So nobody would be willing to put their amount in the bank for 100 years or unlimited number of years. So depositing the amount in the bank is purely an example of a finite arithmetic progression, where first year, second year, third year, fourth year, fifth year, at the most 10 years or 20 years, but we don't put it for 100 or 150 years. So this is an example of a finite arithmetic sequence because the common difference is same. Not only that, the number of terms is limited, 1, 2, 3, 4, 5. So there are 5 terms which are there in the entire sequence. So therefore, in this arithmetic progression, since there are 5 terms, is an example of a finite arithmetic progression. But the same case, say for example, I take set of even numbers. In mathematics, we all know that the even numbers are, say, 0, 2, 4, 6, so on and so forth, where even numbers are generally with the common difference of 2. This is an arithmetic progression because the common difference is 2, where the set of even numbers never end. There are infinitely many even numbers in mathematics. So therefore, this is never ending in the end. It goes on and on till infinity. But this doesn't go till infinity. Therefore, this is an example of finite arithmetic progression, and set of even numbers with the common difference 2 is an arithmetic progression which is an infinite arithmetic progression, and finite and infinite respectively. So let's do some practice problems to study more further on arithmetic progression. To start with an example problem, now, if the question is this an arithmetic progression? So the question here is this an arithmetic progression? Then how do we identify? Initially, I start with finding the common difference. So whenever the question is the given pattern an arithmetic progression, then we find the common difference of each of them. So as I take the sequence here, I clearly see that the common difference of this is 0, and then here it is 0 because 1 minus 1 is 0, 1 minus 1 0, then 1 minus 1 is 0, 2 minus 1 is 1, 0, 1, 0, 0. Clearly, I see that the common difference is not same. It differs because all three zeros, then 1, then 0, 1, 0, 0. So since the common difference is not same, same as I get zeros and ones, therefore the given pattern is not an arithmetic progression, and hence I cannot find the nth term or the first term or the common difference, is how I conclude. Therefore, if the question is given, we identify the sequence to have the common difference same. Common difference not same, not an arithmetic progression. Common difference same, an arithmetic progression, is how we conclude in this case. Now let's see a different type of a problem where we are going to find respectively for the given problem. So let's take the problem here. Now in case of this, the question says, if the seventh term of the pattern (1 by 4) minus 1 by 4 minus 3 by 4 is this, then find the position of the term, this term. So here, as I see the question, it is given that the seventh term is minus 11 by 4, and the sequence or the pattern is given to be 1 by 4, minus 1 by 4, minus 3 by 4, minus 5 by 4, etc. Then I want to find the position of the term. Now position of the term is nothing but finding of n. N stands for number of terms in the arithmetic progression. N stands for number of terms, or it also decides the position of the term. If n is 6, sixth term is the position. If n is 5, fifth term. If n is 17, 17th term, is how we identify the position of the term in the sequence. So n stands for number of terms, or position is what we conclude through the definition of n. Therefore, let's take the solution of this. So the given sequence, when taken separately, let's identify the sequence for their common difference. Now, as I see, the common difference of this two is minus 1 by 4 of minus 1 by 4, which gives me minus 1 by 4. It gives me minus 2 by 4, which is minus 1 by 2. So the common difference here is minus 1 by 2. Now, when I take the common difference of this, also I get minus 1 over 2. Minus 1 over 2. Therefore, since the common difference is same, this is an arithmetic progression, strictly because the common difference is same. Now, when it's an arithmetic progression, it is given that the seventh term of the pattern is this, but before this, my first term a1 denoted by a is 1 over 4, and my common difference d denoted by d is given by the fixed term, which is minus 1 over 2. So using the first term and the common difference, also it's given that seventh term denoted by a7 is given to be minus 11 over 4. So using these three conditions, I'm going to find the value of n, that is the position of the term n. That's how we are going to find. Therefore, as I see that a7 is nothing but the seventh term, therefore the position of minus 11 over 4 in the given arithmetic progression is the seventh position. That means we understand that the an, which denotes with a7, that is n equal to 7, decides the position of the value as obtained. So when I get a7 is minus 11 by 4, makes me understand that the position of this in the given arithmetic progression is the seventh position, is how we identify. But there are some problems where we need to find n where it is not directly given. Though for this example problem, the seventh term is directly given here, but if the question says if the nth term is minus 11 over 4, then how do you find n? Is the biggest question out there, which we're going to discuss in the next coming problem. Now, let's see a problem where we are going to find the value of n, or the position where the nth term is given but the fixed position is not given. So in case of this, let's take a problem where the question says if the nth term of the pattern root 2, root 8, root 18, root 32, so on and so forth, is root 512. Then I want to find the position. Then find the position of root 512 in the given pattern is the question here. So a pattern is given and the nth term is given. I have to find the position of that value in the given pattern. Now this problem is very different from the previous one, because in the previous problem directly the position was given as seventh term and there the position was 7. But here I don't have the fixed position which I need to find. That is, I need to find the position. Indirectly I need to find n. So let's take the problem with the progression root 2, root 8, root 18, root 32, and so on and so forth. Now as I see this, it's very difficult to identify this to be an arithmetic pattern, but I can if I remodify with further simplification. So let's see how I can do that. So when I take the pattern, this is root 2, this 8, I can write as 4 times of 2, 18 I can write as 9 times of 2, 16 times 2, and so on and so forth. So this makes me further simplified with root 2. Root 4 times of 2 can come out as root 4 times root 2, so that this reduces to similarly root 9 times root 2, because root can be split in multiplication. And this is root 16 times root 2, and so on and so forth. So next step, when simplified, gives me root 2. Root 4 is 2 because it is a perfect square. Therefore, I get this as 2 times root 2, which is 2 root 2. Similarly, I have root 9 is 3. Therefore, 3 times of root 2 is 3 root 2. Root 16 is 4. Therefore, I get this as 4 root 2. So on and so forth. So this is the pattern which finally is simplified from the given pattern by series of steps. Now let's identify this pattern to be an arithmetic progression. So in order to do that, we find the common difference. As I see the difference of 2 root 2 and root 2 is root 2, 3 root 2 minus 2 root 2 is root 2, 4 root 2 minus 3 root 2 is root 2, and so on and so forth. So here I clearly see that the common difference is same. Therefore, this is an arithmetic progression. So this being an arithmetic progression, I would like to convert and find the n, or the position, using the formula. So therefore, let's consider the simplified sequence, which is root 2, 2 root 2, 3 root 2, 4 root 2, and so on and so forth. Now with this, I have the first term, which is given by a, and that is root 2, because the first term here is root 2. So a is root 2 here. And the common difference is d, which is the difference of this, which is again root 2. The difference of the term minus the previous term. This minus this, or this minus this, gives me a is root 2 and d is also root 2. Now it is given that the nth term is an, and it is given to be root 512. Now here the nth term is root of 512, which is given in the given problem. Now using this, I have to find the position, that is n. So let's see how we can do that. Now as I go with the formula, I have already discussed about nth term of an arithmetic progression is given by the formula a plus n minus 1 times d, where a is the first term, d is the common difference, and n is the number of terms, or the position of the sequence, is root of 512, which I get out here. Now as I take this, I want to further simplify, but first let me find the possible factors of 512. As we can do using the prime factorization method, I can find all the factors starting with 2. 2 2s, 2 5s, 2 6, 2 1s, 2 2s, 2 8s, 2 64s, 32, 2 8s, 2 4s, 2 2s, 2 1s. 9. So I get this as a. My a is root 2, which I'm going to substitute here. So a is root 2 plus n is something I need to find because the position. So I fix that as n, and times of d, which is again root 2. Therefore, a equal to root 2 and d equal to root 2 are substituted on the left hand side of this. And that is equal to root of 512. I can write it as 1, 2, 3, 4, 5, 6, 7, 8, 9. I can write this as 2 power 1 into 2 power 8, because 2 power 9 can be split as 2 times 2 power 8, is how we get this split using the prime factorization method, is 2 power 9. Now this, on further simplification, gives me root 2 plus n times of root 2 minus root 2, because when I open the brackets, I can split this as n root 2 minus root 2, which is root of 2 into root of 2 power 8, is what I get when I split the factors. And this, on further simplification, gives me these two terms getting cancelled, and I get n root 2 is equal to root 2 times of root 2 power 8 is 2 power 4, because it reduces by half when it comes out of the root. So this 2 power 8 under root is 2 power 4. Exactly half of 8 is 4. And this root 2 and root 2 get cancelled, so that I get n equals 2 power 4, because both sides root 2 get cancelled. And 2 power 4 is nothing but 16. Therefore, my n is 16, which makes me understand from the given problem that n equal to 16 implies the position of the term root 512 in the given arithmetic progression is the 16th position, is how we identify. Is how we conclude. So arithmetic progression is also about finding the position of the term along with finding its first term and common difference. In this case, the term root 512 is identified to be in the 16th position, or is said to be the 16th term of the given arithmetic progression. More mathematically written as A16 equals root 512 for the given problem, is how I understand the question of finding the position of an element in the given arithmetic progression.